All right, AP Calculus, this is 3.5 Implicit Differentiation. Let's get busy. Now, before I even begin, let me tell you what's going on. There are times when we have equations that look like this. And we know what they look like. They're circles, in this case, with a center of 0 and a radius of 2. And I may ask you, for example, to find the equation of the tangent line that passes through 1 square root of 3. And in this case, you look at your equation and you say, you know what? It's not a function. It's not in function form. Can I still find the derivative at this location so I can find the equation of the tangent line? And the answer is yes. And that is what this section is primarily about. Okay. All right. So let's start with some fundamentals. It says differentiate with respect to x. And you'll notice I have some x terms and I also have some y terms. So let's go. If you have x to the fourth, all you're going to do when you derive with respect to x is to do your simple power rule. Okay, so 4 comes out in the front, x to the third, and you are done. Okay, however, if I ask you to take the derivative of x with respect to a y term, okay, then you'll still do it. Okay, however, afterwards, you're going to write the differential in the back, the dy dx. Okay, you could also write a y prime, okay, and that is allowed as well. Okay. If we look at the third one, take the derivative with respect to x. So let's see, this is going to be a 2. Okay. This will give you your 8y, but because I'm using a letter different than the variable x, okay, I have to in the back put a dy dx. Okay. And then finally, this question here says find the derivative with respect to x, and you have x squared times y to the fourth. This time sign is an indicator that we're going to do a product rule. So I'm going to do first times the derivative of the second, and I already know what the derivative of y to the fourth is. We did that over here. Okay. That gives me 4y to the third. Okay. dy dx. Okay. Plus the second, okay, times the derivative of the first. Okay, and the derivative of the first is 2x, and you can stop there. You are done. All right. Very good. All right, as we move on, it says differentiate with respect to x, and you'll notice that I've got a bigger equation, okay? And so I'll just start off at the beginning, find dy dx. Now, this is being done with implicit differentiation, okay, as opposed to explicit, and we'll talk about that in a second. All right, so when I take the derivative here, I'm going to say this is 4y to the third, and put a dy dx behind it because I took the derivative of y. I'm going to do the same thing for the second guy, which is 4y dy dx. I'm going to do the same thing with the minus 2y, so that's minus 2 dy dx. I'll take just the plain derivative of 3x squared here. There's no y attached to it, so this will just be a 6x. And the derivative of 8 is 0. All right, take a moment. Let's make sure I didn't make any silly mistakes because those are easy to do. And I think I'm okay. All right, now what I need to do is solve for my dy dx. Okay, and the reason why is that's what they asked me to do over here, find it. And the way I'm going to solve this by doing 2 steps. I'm going to subtract the 6x to both sides. Okay, and then the second thing I'm going to do is I'm going to factor out a dy dx to all 3 terms. Okay, and that leaves me with 4y cubed plus 4y minus 2. Okay, and then your last step is to solve. Okay, and then you are done. All right, so it's a lot of algebra. All right, you just have to do your basic derivative step like we've been doing for the last couple of days. whenever you take the derivative of a y, as we were indicating through this representation, okay, you'll write a dy dx behind it, and then you'll solve for it. Okay. Now, why do we do it in this manner? Because typically, it's difficult to solve for y when you have so many terms with y here. Okay, you have y to the fourth plus 2y squared minus 2y. It's hard to get y is equal to. That's what we call explicit differentiation. And because it's pretty much impossible to solve for y in this case and get some representation all onto the right in terms of x, we just say, you know, we're going to use this method here, and then in the end, we can solve in a way that makes this more manageable for us. Okay? All right, next one over here. Pretty easy here. We're going to find dy dx, and we'll do so by taking the derivative of each side. So derivative of cosine is negative sine of y. Okay. By chain rule, I'm going to take the derivative of y, which is my angle, and I'm going to write my dy dx since I took the derivative of a y. And the derivative of x is 1. Now, I have to solve for this guy, and that means I'm just going to divide each side by a negative sign. Okay. And the only other thing they may do is this. They say, you know what? Sine in your denominator is really cosecant in your numerator. Okay, and then you would stop right there. All right, so far okay? Hope we're doing well. Let's keep going. All right, you may not know what this looks like. It's been a while since you've seen some of your conics, but the fact that I have a setup here with an addition sign, and both of these terms being the same sign, they're both positives, and a slight imbalance with our coefficients, this being a 4 and this being a 1, means that I have an ellipse of some type, and it does pass through this point. Okay. What I want to know is, what is the slope of the tangent line that passes through this location? All right. So what we'll do is we'll do what we've been doing this entire time. We will take the derivative of this equation. Okay, so if I do that, I'll just do it right below it. I get 8x, okay, plus 2y dy dx equals, and then the derivative of 4 is just 0. Okay, now here's what I do to finish this. I don't solve for dy dx quite yet, all right? I'm going to actually input these values in for x and y, and then solve for dy dx, because I like working with just plain numbers rather than a ton of variables. So here's my x. My x is -1 over root 2, okay, plus 2y, which is root 2, times dy dx equals 0. All right, so this is 8 over rad 2, and that's a negative, plus 2 rad 2 dy dx. And we have to solve, okay? So I will add this -8 over rad 2 to both sides. Okay, and then you'll divide by this 2 rad 2. Okay, now what does that mean? Like, dang, that looks ugly. I'll say this, on an AP test, you could just stop right there. Okay, you've actually solved for it. But imagine this. This is really 8 over 2, which is 4. And you basically have, I'll just kind of show it like this. You can kind of like say, hey, this is your divide, which means you can flip and multiply. Okay, so you cancel those, you get your 4. Rad 2 over rad 2 is 2 in your denominator, and so you'll finish with 2. So oddly enough, when you look at this, this will have a slope of 2 at that respective location, okay? The equation of that tangent line. All right, let's keep going if you got this. So to determine not just the slope of the tangent line, but they want the whole equation. Okay, now you'll look at this and you'll say, hey, what is that shape? And I'm going to say right with you, I have no idea. Okay, but there is a relationship that corresponds with the x and y values, and we'll give you some representation, okay? And I know that the 0.21 will pass through it. When I rewrite my equation of a tangent line, it will take this form. Okay, and the nice thing is I need three things. I need x1, I need y1, and I need m. And two of those three things are already here within my work without actually having to do a heck of a lot. Okay, in fact, my x is 2, and my y1 is 1. Okay, and so all I have to do is find the slope. So let's take a moment and do that, and I will take the derivative of this entire equation. So let's start with this left side. It's going to be a little bit big. This squared button, squared item means I'm going to move that 2 out front. So that's 2 times 2. And I've got x squared plus y squared. Okay. Now, this will go to the first power, which you don't really have to write. But in the inside, you have to take the derivative of each piece. So derivative of x squared is 2x. And the derivative of y squared is 2y dy dx. Okay. Make sure that left side makes sense. Don't forget the chain rule. Okay. I know it gets something kind of ugly, but the reality is that's how it looks. All right. Now the next piece, I have x times y. That is a product rule. You don't really see the times sign visible there, but that's the operation we have to do. So product rule. First, times the derivative of the second. Derivative of y is dy dx. Plus the second, which is y, times the derivative of the x. Okay, I'm not touching the 2. The 2 is out front. Derivative of x is 1. Plus 48, and the derivative of 48 is 0. Okay, so let me pause for a minute. Make sure that that right side makes sense. Basically took the derivative of x times y, and it's done again through a product rule. Okay, now what a lot of people like to do is they like to simplify their algebra and solve for dy dx because that's what you have to do. That is a headache, all right? And it's not that it can't be done. It could be, and it can be accurately done as well. However, here's what I do. I plug in the point first. So here's my coordinate, 2, 1. This is my x, this is my y. Let's be just real careful and plug these in accurately. So this is 2 squared plus 1 squared. Okay, and then I'm going into the part of my chain rule here. 2 times 2 plus 2 times 1 dy dx. Okay, equals 2 times, and again, my x is 2 dy dx, plus y is 1 times 1. All right, I think I inputted everything correctly. And what I'm going to do is I'm going to simplify a little bit. This is 4. 2 squared is 4 plus 1 squared. This gives me 5. 2 times 2 is 4. 2 times 1 is 2 dy dx. This side is 2. And this is 2 dy dx plus 1. All right, now from here, I'm going to simplify it just a little bit more. And once I get it simplified on each side as far as I can go, then I'll solve for the dy dx. All right, so let's see, this is 20. And you're like, that's a lot of steps. And I like to write a lot of steps because it's easy to make a silly mistake. Okay, this 2 means I got to distribute. So I'm going to say 4 dy dx plus 2. Okay, let me distribute this left side here. This is 80 plus 40. Okay, and now it's getting a little bit more clean. All right, so let's do this. Let me move all the dy dx's to the left side. and the items that don't have a term with a dy dx to the right side. So I will subtract 80 to both sides. Okay, so I've got 40 dy dx equals 4 dy dx minus 78. That's right. And then I'll subtract 4 to both sides, and that will give me 36 dy dx equals negative 78. And my last step, if I've done everything right so far, is divide by 36. Okay, and those will go away. I can reduce if I want to. There's nothing that says I need to. But if you wanted to, 2 goes into both of those. I think that'd be 39 over 18. I think that goes in this spot, assuming I didn't make any silly mistakes, and that is a negative. All right. A lot of problem there. Take a look again, just a quick review. Again, be careful on your derivative. Anytime you have a chain rule, make sure you address it. Take the derivative with respect to the y with the dy dx, okay? Another product rule, okay? And again, once you have that, then plug in your point. Don't wait, okay? Don't like try to solve for dy dx when you have all these variables in here. That's a mess, okay? You don't want to solve for that. Plug in your 2 and the 1 appropriately, okay? And again, you'll just work it out. And just looking through my work, making sure it looks good. And again, I think I'm okay on it. All right, very good. If you have any further questions, feel free to ask, but let's move on. Next one says, find the second derivative, okay, f double prime of x. Okay, so where are we at? Here we go. All right, so first derivative, f prime of x is equal to, let's move the 4 out to the front. I don't think I have to do this. I think we've done these before. This is from another lesson. Let's just do it for fun. This is 12 times 2x minus 5 to the third, okay, times 2. All right, and we'll keep going. This is the next derivative. So let's move this 3 out front. So that gives you 36. And that's 2x minus 5 to the second, and times another 2. Okay, so I just kept this the way it was. Just moved that 3 out to the front. There was already a 2 there, but then I got another 2. And so this would be 144, 2x minus 5 squared. All right, I imagine that this is just an extra slide from a previous section, which I kind of caught before this lesson, but I did not catch this one. It snuck in. Sometimes second derivatives do that. They're just like, you know what? We didn't get enough tension in the last lesson. Let's sneak into the next one. There you go. All right, so, well, we know what a second derivative here is another version of that, and it's with a circle. Okay, so if you imagine this is x squared plus y squared equals r squared. So your r here is, your r squared is 4. So you'll have something like this, and so on. Okay? And what I want to know is, what is the second derivative for any point, basically? And so here's what I'll do. I'll just take the derivative. This is 2x plus 2y dy dx equals 0. All right, now here's what I'm going to do further. I'm going to solve for dy dx just because it'll clean up kind of nicely. Let's move the 2x to the other side. Okay, and then to get the dy dx by itself, let's divide by the 2y. All right, and we finish with dy dx is equal to x over y. So what do I do now? I got to do the derivative again. So d squared y over dx squared is equal to, well, here's what I got. I got x over y, which means if I want to take this derivative, I have to use a quotient rule since it's in the form of a quotient. And so it is low times the derivative of the high. Derivative of x we know is 1, minus the high, which is x, times the derivative of the low, which is dy dx, okay, all over low squared, okay. In looking at that, we think, wow, we're pretty much done. And you're right, except I want to do one additional thing, okay. Y times 1 is just y, okay. And there's your x, okay. Now you have this dy dx here, and you're like, well, can I just leave it there? You could, but we already know what dy dx is because you solved for it. It's right here. Okay, so let's substitute. That is an important thing to do, especially on an AP Calc exam. All right, and I'm not going to simplify anymore. It may be that your book does it. Okay, but on a free response test, you can stop. Okay, now, if you're like having a math party and you're like, you know what, I just want to finish this off because it feels just better to my soul. Okay, you'll need a common denominator here. Okay, and then you can get another denominator on the bottom. Okay, and so you'll basically get another denominator of just a y. And so what'll happen is you'll get y squared minus x squared all over. Now there's a y in one denominator, and then you have 2 more below it, and that'll give you y cubed. Okay, so the back of the book may give you an answer like this if you were to check it. But again, an AP test, you stop there. Don't even think about doing more because you don't get any extra points for doing this extra stuff, okay? Awesome. These are my favorite. These are called logarithmic differentiation, okay? And you're like, how the heck would I take the derivative of this when you have an x to a power of some x, all right? There's no rule for that. There is. It's called logarithmic differentiation. Again, it's when you have, oftentimes when you have x's to a power of x. And what I'm going to do is this. I'm going to take the log of both sides, and you can do just a regular log, like of a base 10, or you can do a natural log. I'll just do natural log. Okay, and why do I do that? Well, the big reason is that by rule, I'm allowed to take this power and move it to the front. And that's the only way I can get rid of a power like that. Okay, so from here, you can take a derivative pretty cleanly, all right? So the derivative of the natural log of y is 1 over y dy dx equals, and then here you're like, this should be pretty easy, and it kind of is, but not as easy as some of you may think, because some of you just want to take the derivative of each of these pieces. Remember that there is a time sign there, so that is a product rule. First times the derivative of the second, which is just 1 over x, plus the second times the derivative of the first, which is 3. Okay, that 3 doesn't go with the x. The 3 actually would go out front. And so let's see, I've got 1 over y. I'm going to clean this up a little bit. 3x times 1 over x is just 3. And this becomes just 3 natural log of x. And you're supposed to solve for your dy dx. Okay, so what I'm going to do is multiply both sides by a y. And these guys will go away. And let's see, 3 plus the 3 natural log of x. And what is y? Well, if I go back to my original directions, y is x to the power of 3x, okay? And then you are done. Cool. Let's try it one more time. Even though I don't have powers represented with variables here, it still could be our advantage to do it in this way. Okay, so let's do this. Let's do natural log of y is equal to the natural log of this beast in the back here. So x minus 1 squared. And then this is x squared plus 1. All right, now, why am I doing it like this? Well, I want to separate this. And the idea is that I don't like natural log of this big expression, but I can break this up a little bit. Remember that division okay, of this expression can really be represented through a subtraction problem with a log with each part of the expression. So the natural log of x minus 1 squared minus, okay, the natural log of the square root of x squared plus 1. All right, and now I can kind of do what I did on this other problem with this one with respect to powers. Okay, so this is the natural log, and now I can put the 2 out front. Okay, similarly, okay, this is really, well, it's really just x squared plus 1 to the 1/2. So I'll do that the same way. I'll put the half out front and call this the natural log of x squared plus 1. All right, and now I'm going to get a good looking derivative. All right, so the natural log of y is 1 over y dy dx. Okay, remember that when you take the derivative of a natural log, okay, you just put this guy on the bottom and then take the derivative of that. Okay, now luckily for us, the derivative of x is just 1, and you can just put that on the top, and that's not going to change anything. Okay, similarly, this x squared plus 1 goes on the bottom. All right, and there's a 1 on top, but if you take the derivative of the x squared plus 1, you get 2x. All right, so what happens next? 1 over dy dx equals 2 over x minus 1 minus, well, here's the 2 and here's the half. Those are going to go away. X over x squared plus 1. So I just clean this up a little bit. And let's get rid of the 1 over y. Okay, so let's multiply by y to both sides. All right, and so I'm going to get my dy dx is equal to, and I'm going to have 2 over x minus 1 minus x over x squared plus 1, okay, all times y. And what's y? You're right, it's the original question. All right, so you're going to have to put that into there by substitution. That is not going to give a pretty result, but I tell you what, if this is the answer and you look it up in the back of the book to see if it's right, you see this exactly, you're going to have a huge feeling of satisfaction. All right, so don't underestimate the power of having pure, accurate work. You finish that, oh, cruddy. You finish that and you're like, dang, I don't know if that looks right. It looks too big, but that is it. That's solid. All right. Hey, that's all I have for you. Okay, if you have any questions, you holler at me, you let me know. I'll be happy to help you out. Otherwise, here's your assignments. Okay, it goes kind of quick. Remember that this EOO is every other odd. Okay, so there's just a few there, and I think you'll be able to fly right through it. Okay, again, give me some notice if you have any questions, and we'll talk to you soon.